potential. And we begin by a very brief review of what we did last time. And also, I will discuss how it pertains to the question whether a crystalline solid is a metal or an insulator. So just to remind you what we did last time, we studied a free electron in a weak periodic potential. And in degenerate perturbation theory, well, by examining the first and second order perturbation theory, we discovered that generally when the potential, periodic potential is weak, nothing much happens except for the special points in momentum space and in one dimension. These are special points that are at half of the reciprocal lattice vectors, such as 1/2 of G1. More generally, these will be the so-called Bragg plane or the boundaries of the between Brillouin zones. And what happens at those points when you treat the perturbation in appropriate degenerate perturbation theory, gaps open up at those points, which are proportional to the strength of this periodic potential. So in one dimension, the kind of canonical example is looks like this. You have this parabola, which originally was just h bar squared k squared over 2m, free electron dispersion. And the periodic potential breaks it up into these segments drawn in orange, which are discontinuous, right? And the formation of these energy gaps is really the fundamental result of this band theory. So here, these segments here are called bands, or energy bands. And these areas between them are called band gaps. The meaning of the band gap is that if you look at energies inside of this band gap, say in between these 2 points, right, there are no states allowed in those band gaps. So the energy becomes discontinuous. And as we will see, this has profound consequences for the properties of a solid. So let's now, are there any questions, by the way, about this? So let's now discuss some of these properties, namely metals versus insulators. So a common distinction between a metal and an insulator is that metal is a good conductor of electricity, whereas insulator is a poor conductor or does not conduct at all. So metal insulator is a poor conductor. Now, this is a kind of vague distinction. More precisely, one defines an insulator as a material that in the limit of T goes to 0, namely very low temperature and weak field, electric field in this case, produces no current response. In other words, if you were to define electrical conductivity as a usual ratio between the current produced by electric field, then it would diverge in the limit as temperature goes to 0. Sorry, it would go to 0. The resistivity would diverge, the conductivity would go to 0. So that's a proper definition of an insulator. In practice, things are insulating, or you declare a thing to be an insulator when the resistivity just goes up as you lower the temperature, whereas a metal when resistivity goes down. So a typical distinction would look like this. As a function of temperature, you draw a resistivity, and for a metal, you would expect something that goes like this. So this is a typical metallic behavior. And on the other hand, if it goes something like this, this would be an insulator. Okay? So now how can we relate this behavior to these types of pictures? Let's consider a case when we partially fill.
Actually, Marcel, that should be the conductivity, right?
No, yeah, this is right. Conductivity would have the opposite behavior, right?
Oh, sorry, right.
Yeah, for an insulator, you want to be very resistive, namely conductivity goes to 0. Yeah. So let's consider now a many-body state that we can create by filling these individual states. And let's suppose we have the number of electrons such that in the ground state, we will fill the states up to some Fermi energy epsilon f, which is somewhere inside the band. So let me use some colored chalk. So in the ground state, just like when we constructed the Fermi sphere, we will fill the lowest available energy states with electrons. And this clearly is the ground state of the system. And one thing that we see is that clearly in the ground state, there will be no current in the system. And indeed, that's what you expect if you look at a material in its ground state with no perturbations applied. There's no currents flowing spontaneously. Physically, this is because velocity. So what is current? Current in the material will be given by a charge of electron and the integral dk in one dimension over all occupied states of v of k. And yeah, let me write this as vectors, although in 1D maybe we don't need vectors, but this expression is general. So for each individual electron, the current is simply a product of its charge and velocity. And then when we have many electrons, then we integrate over all occupied states. And yeah, I should write this with a sum. That might be better. So I sum over all the occupied states. All the electrons have the same charge minus E. I'm considering E a positive constant. And I'm summing over this velocity. And the velocity here, as we discussed last time, is 1 over h bar d epsilon k dk. Okay, so for a parabolic band like this, velocity is basically proportional to momentum, right? And in this ground state, the current will be 0 because there's as many electrons with positive momentum as there is with negative momentum. And the way to bring in the current is by taking an electron from this part of the Fermi surface and putting it in here, right? And that way, I would create an imbalance. There would be more electrons with positive momentum, and there will be some empty states at negative momentum. So this will create a current for me, okay? And so this looks like a metal. When I have partially filled band, I can do this easily, right? It costs me just a decimal amount of energy to promote an electron from a state just below the Fermi level here to above the Fermi level there, and I can easily produce a current. So I conclude that metals are solids with partially filled bands, easy to produce. Now, notice that I have not addressed the question, how exactly application of electric field does this, and this we will discuss later when we talk about transport properties in more detail. But it should be intuitively clear that this type of state with a partially filled band is easily transformed into a current-carrying state, because I can easily rearrange my ground state without paying much energy to produce electrical current. Okay? So let's contrast this with a situation when I have a band like this that is completely filled. So now I add more electrons, right? And I can, such that I can completely fill this band. Was there a question?
Two questions. Should there be a factor of m in the expression for V? M over H bar?
I think this is good. So let's check that. So for free electrons, I have epsilon k is h bar squared k squared over 2m. Now I take a derivative with respect to k, so I get that vk is h bar k over m, and this looks good to me, right?
The other question I had was, yesterday when we drew the diagrams, the top band was closed and the bottom band was also extending, like, beyond.
Okay, so this came from a drawing, yeah. So this came from drawing the parabola that I'm looking at, and then looking at the perturbation theory and arguing that I need to consider intersection of a parabola that is the actual parabola and the one that, yeah, remember there was some matrix elements, and I had to look at epsilon k minus epsilon k minus g, right? So I was just examining when this has a singularity, and that's why I drew this additional parabola. But really, I'm doing a perturbation theory for this energy dispersion. So yeah, that's what I'm drawing over there, right? I start with some electron that has states described by this parabola, and then I do perturbation theory, and I ask how does that change, and it changes into this orange thing. Now, as I will talk about later, and as I already mentioned, in a periodic potential, momentum is only defined modulo these reciprocal lattice vectors. So what you often find is that people in condensed matter physics almost exclusively would shift these branches back into the first Brillouin zone, getting pictures like this. And this is the well-known reduced zone scheme, and often you find this, or almost always you find this in the literature, and I will talk about that still. But we need to conserve the number of states, right? We start with one parabola, and then it breaks up to these segments, so we don't want to draw all these other parabolae, which are there just for illustrating where this denominator vanishes. Okay? Any other questions? Okay, good. So let's get back to this case when I have a completely filled band, right? And now, again, it's clear that in this ground state, there will be no current, generally, because I have as many states with a velocity moving that way as in the opposite way. So this is not a current-carrying state. But also, in this situation, it's not so easy to create a current carrying state, because in order to do that, there's no available states for me to manipulate, right, other than those in the next band. So the easiest accessible current carrying state would be one where I take electron from here and promote it either up here or there. Okay. Now, there's two problems with that. This costs a finite amount of energy. So when I just apply, when I'm at low temperatures and I apply a very weak field, then this should not supply sufficient amount of energy to overcome this gap. And second, these states here that I'm talking about actually don't contribute to the current, because you can see that they come in with zero slope. And therefore, their velocity is actually zero. You would find that velocity is proportional to the derivative of energy with respect to momentum. And so interestingly, these states here near the boundary of the Brillouin zone also have zero velocity. So this looks like an insulator. And indeed, insulators are solids with completely filled bands. And in this case, weak field cannot produce current. Okay? And indeed, I will show you some examples of band structures for metals and insulators, and we will see that in each case, this rule is satisfied. Now, here's one last thing that I want to mention, which is kind of a quantitative description, more quantitative description of when a material can be a metal or an insulator. So we said last time when we discussed Born-von Karman boundary conditions that the number of independent momentums or number of allowed momentum values in the first Brillouin zone is equal to the number of unit cells in the crystal. And let me just remind you of that, or let me write that down again, because this is an important statement. Number of allowed K values in the Brillouin zone is equal to the number n of unit cells in the crystal. And this is an important consequence, this statement, for the criterion when a system can be a metal and when it can be an insulator. So what this implies is that one needs an odd number, an even number of electrons per unit cell to have an insulator. Why is that? Well, so here in the first Brillouin zone, or in any other Brillouin zone, there's exactly n allowed values of momentum, meaning I can put in 2n electrons here. And this 2 stands for spin, right? So spin I've been ignoring so far because it doesn't really do anything, but now I have to put it in because into each independent value of momentum, I can place electron with spin up and electron with spin down. So a filled band contains 2n electrons, where n is the number of unit cells in the crystal. Question?
When you're saying in the crystal, do you mean the born from Fermat?
Yeah. So I have a crystal which contains n unit cells, n1 in x direction, n2, n3, and n is the product of the 3, and that's the number that I'm considering here. So once again, 2n electrons fill each band, and clearly if the number is different than some even integer times n, then I will have partially filled bands, right? And then I will have a metal. However, this is only a necessary but not sufficient condition to have an insulator Why is it necessary but not sufficient condition? It's because you can have a band overlap. So for instance, imagine you have a situation, something like this. Imagine you have one band that looks like this, and then you could have another band coming down like so. This would not occur in this weak potential approximation, but generically, there's nothing to prevent this type of band structure to occur. And so now if you put in, say, 2n electrons, you try to fill in this band, and you say, OK, this is an insulator. But this is not really a ground state of the system, because you see that there are these states here below this line, which you can now fill instead of these states and lower the system's energy. So in fact, the correct ground state here with 2n electrons would look like this, and some of these states filled, right? So the chemical potential is somewhere here. And this clearly has two partially filled bands, although it has 2n electrons. So this would be a metal. And therefore, this is a necessary but not sufficient condition for having an insulator. Nevertheless, there is lots of insulators in nature, so this condition is often satisfied. OK, I'd like to now present a slide. So whoever sits in the booth, would you be so kind and give me the projection equipment? OK, I can do it myself sometimes. Yes?
Is it also possible to, if you have even number of electrons, is it also possible to have a metal with even number of electrons per conductor, which will just not have fully filled the first band, and therefore, you know, with no gap overlap, just like with the simple one.
Yeah, I'm not quite getting your question.
So,
sorry.
You were saying that the only way that we can have even number of electrons and still have a conductor is if you have a band overlap.
Yeah.
Can it also happen that you just like not have filled the lowest band?
You want to leave some of these states empty and put some electrons here?
No. Just the argument that you said that I make in a like non-equilibrium.
OK. So you're asking, is it somehow possible to have a skewed band structure, something like this?
No.
Well, yeah, I'm still not getting your question. Sorry.
My energy, the epsilon f, will be just somehow not on top of the end of the first band, just somewhere in the middle, as you drawn it before. The epsilon f you drawn before.
Yeah, like this.
So that will, even if I have even number of electrons, right? I can just like.
Well, no, but then I only have if I look at the momentum, if my EF is here like I drew it before, then I only have these momentum states filled, and that's clearly less than 2n electrons, right?
Oh, and is like given from the.
Yeah. Once I specify my crystal, then there is a given number n of momentum states that cannot change until I change my the size of my crystal. Let me just dim the lights. Okay, so here's, this is not directly related to what we were just saying. This is one slide about magnons that we discussed a couple lectures back. So what I'm showing here, remember we discussed ferromagnetic magnons 2 lectures back, and we derived dispersion of ferromagnetic magnons, which we showed was quadratic in momenta. And here's some measured magnon dispersion. This is for magnetite, which is an oxide of iron. I think it's Fe2O3, if I'm not mistaken, a kind of classic ferromagnet that you find in nature. It's basically this rusty-looking rock that is magnetic, and indeed the measured dispersion at low momenta is quadratic here. And once again, this is neutron scattering by Bloch. So this is made in Canada, proudly. Another thing that I'm showing here is the heat capacity. In this case, this is yttrium iron garnet, which is another ferromagnet. And the nice thing about this is that it's an insulator. So there's no contribution from electrons to specific heat. So the only contribution is specific heat of phonons and magnons. And again, the way to disentangle the two is to plot the measured heat capacity as a function of T to 3/2. And the quantity that is plotted is specific heat divided by T to 3/2. And in this representation, straight line here will give you the phonon contribution, and the intercept here at T equals 0 gives you the magnon contribution, showing again that this T to 3/2 that we found is experimentally observable. And that there's other experiments that you can find in the literature which show this type of thing. Okay, so this is some magnon data. And now back to electrons in weak periodic potential. So I just want you to remind you of this construction that we did yesterday, electrons in weak periodic potential. Once again, we start from this parabola. We do second-order perturbation theory and find that even weak periodic potential has a strong effect at these points of degeneracy, which correspond to 1/2 of reciprocal lattice vector. And then we do degenerate perturbation theory and find that this is the result of that calculation. A gap opens up, so the resulting spectrum then looks like this. However, we have to do the same construction for all such points of degeneracy, and this results to a broken up parabola, just like I drew previously. This is maybe a bit nicer. Now, often what people do, well, so this is a band, this is a band gap, and this is what is called in the literature extended zone scheme. So the momenta here run from -infinity to infinity. However, as we said, once you break translational symmetry, momentum is no longer a good quantum number, is not really conserved, is conserved only modulo these reciprocal lattice vectors. So one is allowed to actually shift these individual segments into first Brillouin zone by shifting each momentum by the appropriate reciprocal lattice vector. And this also follows from Bloch theorem. And then one gets a picture like this, which is called reduced zone scheme. Bands are folded into the first Brillouin zone. Once again, this segment has been shifted into here and results in this segment. Similarly, this segment has been shifted here and results in this. And this is what you will find almost universally in the literature, just because it's a more compact description. It trades a description in which each state is uniquely labeled by a value of k into a description where k ranges in the first Brillouin zone. And then you have a multiply defined function. So these are the bands that would have index n equals 1, 2, 3, 4, and so on. Right? It's the same number of states, just plotted in a different way. So things get more complicated once you go to higher dimensions. So far, we discussed just one-dimensional example. In higher dimensions, I cannot really draw anything on the blackboard, but I will show you some examples here. So in 2 dimensions, a canonical example is graphene, which is an atomically thin layer of carbon atoms forming a honeycomb structure. And you will actually do this in one of the tutorials next week. You will find the band structure of a simple model for graphene. And in this case, of course, the Brillouin zone is 2-dimensional. It's a Brillouin zone appropriate for this honeycomb lattice, which is a triangular lattice with a 2-point basis. So the Brillouin zone, first Brillouin zone, can be drawn as a hexagon. And then energy dispersion can be drawn as an energy surface in this first Brillouin zone, right, which is drawn here. This is what one finds for the energy levels closest to the Fermi level. It has these points where the two touch. So this is neither an insulator nor a metal, but something called semi-metal. And it has many different interesting properties. An alternative depiction of this band structure, which is also useful in 3 dimensions, is to choose some path in this Brillouin zone. In this case, they chose a path from this endpoint in the corner to gamma, and then from gamma to k. And then you plot the energy along those lines. And it results in this type of band structure plot, sometimes also referred to as spaghetti diagram because of all these tangled lines. And to make any sense of it, one has to remember that, again, in the literature, almost always 0 energy refers to the Fermi level. So all these states here would be filled. All these states would be empty in the ground state. And to make a contact between this plot and this plot, we identify the 2 bands that are plotted here with these 2 bands. So these are the 2 most important bands that meet at the Fermi level. And at low temperatures, most of the physical properties of graphene will be given by these 2 bands because, of course, at low temperatures, you have only small amount of energy available for excitations. Notice the scale here. This is electron volts. So this is 10 electron volts, which is roughly 10,000 Kelvin. If you're at a room temperature, a couple hundred Kelvin, basically the energy scale that you're looking at are very close to this line. And for all practical purposes, you can forget about these bands and those bands because they are just either filled or empty. And there is no possibility of changing that occupancy because the energy that you would have to supply corresponds to tens of thousands of Kelvin. And by then, the whole graphene would melt. So often, it's enough to just consider the situation of very close to the Fermi level. Any questions? Yes?
So since there isn't any actual band gap, why do we not call it a metal completely?
Well, because it does not have a Fermi surface. So typically we call a metal, and maybe I should have emphasized that, in higher dimensions, something that has a Fermi surface, like a Fermi sphere in 3D or a line in 2D. This is a kind of anomalous because a Fermi surface has sort of shrunk into a point. And another way of saying that is that the density of states at the Fermi level in a metal should be non-zero. And here it, in fact, goes to 0. Although just above and just below Fermi surface, there are states. Right at the Fermi surface, it vanishes. So it's this marginal case between a metal and an insulator, and we call it a semi-metal. And it has some interesting transport and other properties that are reflected by this. OK, so in 3D, things become even more complicated, although the idea remains the same. It's just that visualizing these band structures, now I have, say, for an FCC lattice, which is a very common lattice in elemental metals and insulators, I have a three-dimensional Brillouin zone like this. So in principle, I should specify the energy everywhere inside of this three-dimensional body, and that I cannot really visualize in any reasonable way. So the way this is done is almost exclusively through these spaghetti diagrams. One denotes some high symmetry points in the Brillouin zone with this gamma typically denoting the center of the Brillouin zone. And then one chooses some path. So from center of the Brillouin zone to X, from X to W, then to L, and so on. And then along those lines, once again, we plot the energy dispersion. And what is plotted here is simply, so this is not really a band structure of anything. This is simply k squared, h bar k squared over 2m plotted along those lines and folded into the first Brillouin zone. So you can see that if you had a metal that didn't have any periodic interactions, then the band structure would look like this. Now, the construction that we discussed last time with weak periodic potential instructs us that at these points, at the Brillouin zone boundary, where we have these degeneracies, we should impose a small gap. That would be the effect of those perturbations. And indeed, this is borne out. So once again, this is bands for an FCC lattice in zero periodic potential. And this, for comparison, is the actual band structure of aluminum. So what you see here, and this is kind of, didn't come out as clearly as I was hoping. So there's two kinds of lines. There are these thin lines that you can barely see. And these are basically the same lines as here, just copied from that picture. Whereas the darker lines, thicker lines, are the actual lines for aluminum. So you can see that down here, near the gamma point, which should be compared to this, it's just a parabola. And it's extremely close to this non-interacting or zero potential situation. However, at the boundary of the Brillouin zone, where there would be these degeneracies, actually there's quite a sizable splitting in aluminum that comes from the periodic lattice. But nevertheless, aluminum is a kind of poster child for this weak potential approximation. It works very well. You can actually, in your free time, if you're interested, you could calculate this yourself by just putting in some periodic potential that is appropriate for aluminum and getting these graphs. Things get more complicated in other metals. OK, one more thing. Aluminum clearly is a metal, and this is borne out in this calculation. The chemical potential is here, and so it intersects some bands, and therefore there are partially filled bands, which suggest this is a metal, and indeed we know that aluminum is a good conductor. Here's another example. Yes?
Can I just ask, how can we, or can you give some trivial example of such weak potential, or how can we like picture this like weak periodic potential? Is it like some external field we apply, or is it within the crystal we were talking about?
Oh, so the physical origin of this periodic potential, of course, is the ionic lattice, right? And the kind of very simplest, I mean, if you were to do this naively, then you could just take FCC lattice of ions and consider their Coulomb potential added up. And you would have to include some screening effect to avoid singularities, because Coulomb potential would be singular at the center. And then you would put it in, and you would get something quite similar. Now, for aluminum, that would work reasonably well, because it's such a simple metal. For other structures, there are many more sophisticated methods that there's a whole industry in calculating these band structures accurately, and there's literally dozens of sophisticated methods that one can apply that have various cryptic names like muffin tin potential and pseudo-potential approximation and LAPW and so on and so forth. And if you're interested, there's a whole chapter in Ashcroft and Mermin which gives a description of these various methods, at least a kind of qualitative description. But we're not going to really study that, because our goal is not to make you into band structure specialists, just to understand the basic idea. Yes?
I'm just curious how experimentally they get these amazing band structure measurements, like along different paths in the material design and stuff.
Okay. So there's a number of powerful methods that probe band structures. The kind of classic method is the so-called magnetic oscillations method, and or de Haas van Alphen method. And again, this is something that is usually extensively discussed in an undergraduate course, but I will not have time to discuss it here. There's a number of more modern methods that give band structures very directly, and one of them is angle-resolved photoemission. Basically what you do, you take a material and you shoot light into it, and you emit electrons because you give them some energy. And by analyzing which way these electrons go and what is their energy, you can back out precisely this relation between momentum and energy in the crystal, and you can plot these bands with high accuracy. And there's other methods that have been applied over the years to these materials. What I'm showing here, though, I have to emphasize, these are all calculations. These lines, and for aluminum as well, these are calculations. They are believed to be accurate because they were compared to experiments, but yeah, these are all calculations. Anyway, this is a band structure of germanium. This is a technologically important semiconductor, which in its pristine state is actually an insulator. So you can again see, once again, this parabolic dispersion at the bottom near the gamma point. But then you can see that the gap here, for instance, is larger than in aluminum, which tells you that the weak potential approximation is not really maybe working as well. And then there is much rearrangement of bands compared to weak potential approximation case here. And the important thing is that there is a gap, right? Everywhere between, say, 0 and 1 electron volt, there's just no states available. The Fermi level is such that these states are filled, those states are empty. So in its pristine state, germanium is an insulator. Its use in semiconductor industry comes from it being doped by some other metal with a different valence, which either removes some of these electrons here or adds some electrons into the conduction band and makes it slightly conducting, and that's what makes it useful as a semiconductor. Another important material technologically is silicon. Once again, it's a similar situation. Down here, it looks parabolic, just like you would expect. However, here in this region, the periodic potential has a stronger effect. And again, pristine silicon would be an insulator there is a band gap of about 1 electron volt. And again, you can dope it with boron or something and remove some of the electrons here or add some of them there. And then it acts as a N-type or P-type semiconductor. And all our computers, including my laptop here, are based on this silicon. OK, any questions about this? If not, then can somebody please turn on the lights? I will continue on the board. And can we have the screen raised? Thank you. OK. So as I mentioned, calculating band structures of materials is a veritable industry, and there is specialists at universities who specialize in this. There is companies out there who develop numerical codes that can be used to calculate these band structures and so on. And this is a useful thing, right? Because in the semiconductor industry, you want to know what is the band structure of your materials. In other fields, in materials research, you want to know what your materials look like and at the atomic level. And yeah, again, we can only scratch the surface. So we discussed this weak potential approximation as one method, which kind of explains how the gaps open up. But to do better, one has to go beyond that. I'm going to discuss one other method, which is called the tight binding model, which is in some sense complementary to the weak potential approximation, because it works in the situation when the periodic potential is actually very strong, and it's the kinetic energy that will be taken as a perturbation in this case. One virtue of this method is that one can often solve everything exactly by hand and get simple models that show interesting properties. So basically, the idea is like this. I have a solid where I have my ions in some periodic arrangement, right? And now let's just plot the potential that one expects to be generated by this periodic potential, by this periodic lattice. So this is my U of R, which is clearly periodic. And since these can be thought of as point charges, the potential is Coulomb, so it's divergent, right? If we now think about a situation when the interatomic spacing is pretty large, then to the leading approximation, the levels in this potential are basically atomic levels, right? So we can just solve for each atom separately, and this solid is a kind of a funny collection of just basically individual atoms with no common structure, and indeed some inert gases like argon solid, argon solidifies at very low temperatures. They would look a little bit like this. So in our description, instead of starting from independent electrons roaming around, we take as a starting point these independent atomic orbitals. And then, however, we think about the overlaps, right? So each of these states, let's say this is the lowest state of these atoms, some s orbital, there's some wave function associated with it, centered at the atom. And there's another one centered here. And there will be some small overlap when you bring these guys close together. In other words, what will happen between these two wave functions is that they will start hybridizing. Instead of this wave function being a good eigenstate of the system, it's going to be some superposition of the two, and that will then reflect on the energy of the system. And that, of course, happens with all these wave functions. If you bring them closer together, there's some small overlap here, but we will be thinking about a situation, and that's the name, the tight binding model. All these electrons have wave functions that are tightly bound to their respective atoms, and we treat their overlaps as a perturbation. So to write down some equations, let's write the Hamiltonian for a single electron in this situation as h bar squared over 2m Laplace squared plus, and we write this periodic potential as simply sum over all the atomic potentials. So this U of r is just a potential associated with a single atom. Okay. And then let's consider atomic wave functions. And let's call these phi n of r. And these are solutions of individual atom Hamiltonian where H atomic is simply a Hamiltonian associated with a single atom that goes into that construction. Okay. And so instead of expanding in the system of plane waves, as we did before for nearly free electrons, we now expand in these eigenfunctions. Okay? So let's move to second quantization. And in second quantization, let's define an operator C dagger n I, Ri, as the one that creates electron in orbital phi n r minus Ri. And again, I'm suppressing the spin variable because spin is just there for a ride. And sometimes I will associate with this also a vector in Hilbert space like this. I will use those interchangeably. Okay? So once we have this, we can right away write down the second quantized Hamiltonian simply like this, just following the recipe that we always follow. This. So I have to calculate the matrix element n Ri of this full Hamiltonian M Rj, and then do this. Now, let me just mention a caveat here that is very important if you want to get things quantitatively right, but qualitatively we're okay. So notice that if I take as my basis all these states, this is not really a legitimate basis because these states, first of all, are overcomplete, and second, they are not really orthogonal. Okay? So notice what I have done. I have solved a Hamiltonian for a single atom here, right? And these are these eigenfunctions phi of n. So they would form a complete set of wave functions, and they would also be mutually orthogonal, or I could make them orthogonal if I want them to. However, as my basis for second quantized Hamiltonian, I'm taking those wave functions plus all those at all other atoms. So clearly this is an overcomplete basis, plus there's no guarantee that two wave functions associated with two neighboring atoms are mutually orthogonal. So strictly speaking, this is really not a right way to proceed. Now here's the mitigating circumstances. I will only use a few eigenstates of each atom, typically just say just the s orbital from each atom. So this overcompleteness doesn't play any role. I will, for instance, not put in any continuum states that are not bound states here. Second, this fact that they are not orthogonal, that can also be dealt with by taking some appropriate linear combinations. What it leads to is a formalism that is kind of complicated, but in the end, it leads to the same result that I'm going to get here. So if anybody's interested in a more rigorous version of this, Ashcroft and Mermin gives a good discussion. But yeah, I think to just get a gist of it, it's better to avoid all those complications. And let's just say that these orbitals that I'm using are nearly orthogonal. And if I really wanted to, I could orthogonalize them properly. But the price I pay is then that the calculation becomes non-transparent. So yeah, just to say that the way to do it is take some linear combinations of these guys with appropriate coefficients. And the result of that calculation is that to make them orthogonal, there's still a dominant contribution from an on-side wave function plus some contributions from everybody else, which are all small. So I could go from here to some wave functions phi tilde n of r minus ri, which are already properly orthogonalized. Just the expression for them is kind of messy, so I don't want to mess up with them. But if this bothers you, then let's think we already did that, and we're using these orthogonalized wave functions, and the result will be the same. So anyway, with those caveats, this is what people call tight binding Hamiltonian. In general form. And for it to be useful, we need to make some statements about these matrix elements, right? Clearly, if I have to sum over all different eigenstates of each atomic orbital and over all I and j positions of all atoms, this Hamiltonian is not useful because I just have some hugely complicated, everybody is connected with everybody, so I cannot really solve it. But if I make few plausible assumptions, then this can be vastly simplified, and it's extremely useful. So the first assumption is that only wave functions on nearby orbitals or nearby sites have appreciable overlaps. And this is just saying in words what I drew here. Basically, we know from atomic physics that the wave functions of bound states decay exponentially on the length scale of roughly the Bohr radius. So basically, if I think about the overlap between this wave function and that, it's something, and the overlap between this wave function and second nearest neighbor is suppressed by a factor that is exponentially small in this distance. So typically, I only have to consider nearest neighbor, potentially next nearest neighbor's overlap, and then I neglect everything where the distance between I and j is larger than that. And second, and this assumption is slightly less well justified, but we nevertheless use it, wave functions for different overlaps, for different atomic orbitals i.e. n is not equal to m, have different symmetries and therefore again overlap is small. Okay? And this is an assumption that is valid mostly, but there are important examples where there are situations where everything else vanishes, and since these guys are small but not zero, they play a very important role. But again, in the very simplest applications that we're after, this doesn't really show up. So we will use that as an assumption as well. Okay, so let's now proceed. Basically, we want to simplify this matrix element based on these assumptions. And for that, let's write the Hamiltonian in the following form. We write it as H atomic with index j plus delta u j of r, and this delta uj of r is sum over k not equal to j u r minus rk. So basically, I'm separating the full Hamiltonian into a Hamiltonian of one atom that I call J, so that's one of the atoms in the system, and then the potential of everything else. So here I'm summing over all sites in the crystal except for that site. And this will be useful in the subsequent manipulations. So let's write that matrix element in Ri H and Rj. This is just integral in three-dimensional space, and I write these wave functions phi in R minus Ri, H atomic J plus delta Uj of R phi R minus Rj M. This is how it looks. And you see what I'm about to do. Basically, I chose this decomposition of the Hamiltonian in such a way that H atomic J acts on the wave function that is centered at that atom. So this can be replaced by just the energy eigenvalue of that, and I'll be left with just the potential part. Okay, so I can write this. Once again, I'm acting with this Hamiltonian there, and I just pick up an eigenvalue Em. So that's here, and I'm left with D3R phi star n R minus Ri phi m star R minus Rj. So that's the first term, and the second term I just have to copy there's not much I can do with it at this point. Like this. Okay. But I at least simplified the first term. So now let's distinguish the cases when I is equal to j and I is not equal to j. Those will behave in a qualitatively different fashion. So let's start with the case I equals j, meaning I'm calculating the matrix element between two states living on the same site. And in this case, the first line here now refers to the same atom. So I can calculate this integral simply by orthonormality. And the first term is simply Em times delta and m, because those are orthonormal. And the second term is, well, I can just, basically what I'm going to do, I'm just going to shift it. I will just assume that my Ri is at 0 so that I can write it in a simpler way. And this then looks like follows. As follows delta U of R phi m of R. Okay? So I just shifted everything to the origin. And if you look at this structure, basically what I have is a wave function times the wave function at a given site. But this is a potential coming from all other ions except the one that I'm looking at. So if this is my origin, then basically I'm looking at a product of some wave functions at this site and then multiplying it by the potential from all other sites except for this one. And clearly, this will be a small contribution because the wave functions and these potentials are centered at different sites. So I declare this to be small. And typically, it's going to be much smaller than this energy eigenvalue. And to leading approximation, I can neglect this. OK, so when I is not equal to j, then this combined point 1 and point 2 in our assumption allows us to write this expression as follows. Well, basically, in this case, I cannot really simplify this any further. All I can say is that these overlap integrals decay exponentially with distance. So, according to the second assumption, whenever n is not equal to m, the overlap is relatively small. So I approximate this by delta n m times Tij with the proviso that this Tij decays as e2 minus Ri minus Rj over A0, where A0 is the Bohr radius. Is there a question?
Use the word in the second part. Different atomic orbitals have different something.
Different symmetries. Okay, and so in order to now calculate these guys more accurately, one really would have to go to atomic physics for a given atom, put in the wave functions of these orbitals, and do some numerical calculation of these overlaps. But this general property will be true. And although I'm neglecting the overlaps between orbitals with different symmetries. In general, again, they might not be zero. I'm just saying that generally they will be smaller than the overlaps of the like orbitals which have the same symmetry. Okay, so let's now give some examples of where this method becomes useful. And the simplest case is that of a single non-degenerate orbital. So I'm assuming that each of those sites has just single s orbital, which is non-degenerate. And I want to write down the tight binding model simply on the grounds of symmetry. If I have just a single orbital per site, then I can write it like this. Sum over I. I have some energy for the on-site potential, which is just the energy of the atomic orbital itself, C Ri, C Ri, plus, or rather minus, and I will explain this, sum I not equal to j, Tij, C dagger, Ri, C Rj. Okay. The minus sign here is conventional, and I should also put it in here. Put a minus sign. Typically, it turns out when you calculate these overlaps, because of the properties of the wave function and the potential, they come out negative. Not always, but in simple cases, they come out negative. So I consider this to be positive numbers typically and put a minus sign there. This is the way to write down this, this thing. So one can solve this actually in full generality, but let's just consider a simple nearest neighbor tight binding model. Which means that I will explicitly consider only overlaps between the nearest neighbor sites of some lattice and neglect everything else, which means simply that Tij is equal to some T for Ri, Rj being nearest neighbors and 0 otherwise. Okay. And let's consider, for simplicity, also a square lattice. So I have a square lattice like this, and the nearest neighbors are obviously these guys here, right? So I take a site, and its nearest neighbor is, it has 4 nearest neighbors. If it's a 2-dimensional square lattice, I could do that in 3D. It would have then, in a cubic lattice, 6 nearest neighbors. And the Hamiltonian, in this case, can be rewritten like this. So quite generally, I can rewrite the second term like this. Instead of summing over sites I and j, I just sum over all sites I and then all the neighboring sites. So this would be a typical vector delta. And so for instance, in my square lattice nearest neighbor model, this delta there would be 4 independent deltas along x, y, and z. But I can proceed there completely in complete generality. I could include, if I wanted to, the second nearest neighbor hoppings and so on. This Hamiltonian can be solved for all of those. Any questions, by the way? OK, so this is, again, a periodic structure. So I expect that going to a Fourier space will simplify this Hamiltonian. So I Fourier transform. And what I do, I write C of r I as 1 over square root of n sum over k e to I k dotted into Ri times C of k. And similarly for C dagger, I substitute this into the Hamiltonian. And we did this before in the case of phonons, but let's just do it again in this case. So the first term looks like this. So this is the first term, and the second term will give me this. Okay, so the important thing that I notice here that in both of these terms, I have an expression like this, and the same thing in here. So I can immediately perform summation over these real space positions. And as usual, this thing gives me just delta kk prime. Once I have that, I can simply use that delta kk prime to perform, say, k prime summation in these guys. And the result of this operation is that I have a Hamiltonian that is just sum over a single wave vector epsilon k, c dagger k, ck, and this epsilon k is E naught minus some over delta t delta e2 minus ik dot delta. This is what is called tight binding dispersion. And notice that this solves the problem for arbitrary t's, right? I didn't really use this assumption that it's just nearest neighbors. I'm going to use it shortly, but for arbitrary set of t's that connect these sites, I can solve this tight binding model just by performing this summation over all neighbors, and this is a simple mathematical operation. So this is why tight binding model is extremely useful. One can get the solution by hand in almost all cases. Okay, any questions about this? So let's now revert to our example, nearest neighbor tight binding model on the square lattice. So in that case, nearest neighbor square lattice I have deltas that are plus minus ax and plus minus ay, right? So this sum then, and all t's are the same, t delta are simply just the same t. So in this sum, I just have 4 distinct terms, and I can add them up. And you can see what happens. I get e to the ikx plus e to the minus ikx. That gives me cosine in both kx and ky. So the tight binding dispersion for a square lattice model with nearest neighbor hoppings is simply looks like this. Cosine a times kx plus cosine a times ky, and this is a classic dispersion. If you want to play with this, you can ask, for instance, if you add the second nearest neighbor hopping. So if we call this one t, we can call the second nearest neighbor t prime, and one can see what that leads to. There will be a term proportional to t prime, which will have some products of cos k. It will have terms like cos kx plus ky, cos kx minus ky, and so on. And one can plot those dispersions and play with that. Okay, so let's just, as a last thing that we do today, briefly analyze this tight binding model on the square lattice with nearest neighbor hoppings. Yeah, we can do several things. For instance, we could plot that if we had a 2-dimensional plotting routine. We could plot that whole dispersion. I can attempt to plot it here as a contour plot, which is not going to be extremely good. So this is my 2-dimensional Brillouin zone. This is kx. This is ky. This corner point, for instance, is pi over a. And then this cosine dispersion looks like this. At the center of the Brillouin zone, it's basically parabolic because you can expand it for small k to second order, and it's basically a parabola. Similarly, near the corners, it looks like the top of the band. So let me draw this. Then in the middle, actually, there is one contour that looks like a diamond, and then it continues like this. So this is the tight binding dispersion where there is a maximum here, and minimum is over there. And you can see that because of this minus sign here, when kx and ky are 0, then of course this is as small as it can get. Another thing that one can do, one can plot this as a function of just kx. So I plot along this line here, and the dispersion then will look like this, just a cosine, right? like this. A few other things that, that we can note. So one can extract from this, for instance, the minimum energy of the band. And this is epsilon naught minus 4t. This occurs at k equals 0. Maximum is epsilon naught plus 4t. This occurs at k equals pi over a, namely the corner of the Brillouin zone. People often talk about the bandwidth W, which is simply epsilon max minus epsilon minimum. This is called bandwidth. And in this case is equal to ht. One other thing that is kind of fun to plot, I can plot the band velocity Vk is 1 over h bar d epsilon k dk. So this is a vector which is 2t over h bar times a. And it's a two-component vector, sine a kx, sine a ky, like this. And it's a fun thing to plot this band velocity, which I can plot in a different color here. And it looks like this. So this is v of k. If I just plot it along this one line, again, it's a vector field which is defined everywhere in this two-dimensional Brillouin zone. So I don't know how I would plot it there, but if I just plot the amplitude of the velocity along this line, then it looks like this. And notice the following interesting thing. So for free electrons, Vk would be simply h bar k over m. Namely, velocity is normally proportional to your momentum. And indeed, this is born in this region of the Brillouin zone, right? You increase momentum, and indeed, velocity in this case is proportional to it. However, about halfway to the boundary of the Brillouin zone, the thing reverses, and in this region here, there is a kind of perverse relation between momentum and velocity. Namely, you keep increasing momentum, but the velocity keeps decreasing, and at the boundary of the Brillouin zone, it goes back to 0. And this is a kind of illustration that in motion in periodic potential can be quite counterintuitive. You're kind of increasing momentum and the velocity is decreasing. And that's simply because this is not a free particle. It's a particle that moves in a periodic potential. And in addition to forces, if you think classically, in addition to forces that you exert on a particle, there's forces exerted by the lattice. And in this case, those are such that in these regions of the Brillouin zone, the relation between velocity and momentum is counterintuitive. I think that is all that I wanted to say today. Are there any questions? If not, then I see you all tomorrow. Thank you.